Okay, welcome to the second to last fall 2009 Nokia Distinguished Lectures on Cyber-Physical Systems, which are organized this semester by CITRIS, the Center for Information Technology and Research in the Interest of Society, and CCIT, the California Center for Innovative Transportation. My name is Alex Payen, and I'm in Systems Engineering over in the C department. So this lecture is currently being broadcasted live to the three other CITRIS campuses, Merced, Santa Cruz, and Davis. So if you're watching us online and you want to ask questions, you can IM us your question at the very end of the seminar. So let me say a couple words about the Nokia Distinguished Lectures on Cyber-Physical Systems. These lectures are subsidized by Nokia and are specifically focused on problems to do with cyber-physical systems, which are systems integrating both computation and physical processes. And I think this week was a particularly exciting week because the Mobile Millennium Cyber-Physical System just went up, and this is really how the genesis of these lectures was created. So if you want more information about the lectures as well as about Mobile Millennium, you can go to traffic.berkeley.edu. Before I introduce this week's speaker, let me say the last lectures of the series will be Professor Jerry Marsden from Caltech, and he will be talking about discrete mechanics and optimal control, and that will be on November 25th in this room at noon. So today, it's my pleasure to introduce Professor George Pappas, who is the Joseph Moore Professor in the Department of Electrical and Systems Engineering at UPenn, former director of the GRASP Lab, and who currently serves as the Deputy Dean in the School of Engineering and Applied Science. George is a former alum from Berkeley, where he got his PhD in electrical engineering in 1998. And he's a recipient of numerous awards, which include the Curio Award and the Picasso Award. And in fact, great news just happened yesterday, as I understand. George was just elected as a fellow of the IEEE, and for which we should all applaud. And welcome, George, to Berkeley.
Okay, thank you. It's a great pleasure to be back. And I'd like to congratulate the Berkeley team, especially for the phenomenal success of the Mobile Millennium project, which was really amazing. I should also thank Alex for organizing, inviting. It was really a very luxurious visit, and I'm enjoying it. I had my personal mini conference this morning, which was great. I should also thank my students, my group, and a lot of my collaborators and sponsors that have contributed a lot for this what I'll present today, but I'm not going to present everything that they do. In fact, let me start by saying some things that I'm not going to talk about too much, and half of it has to do with more distributed robotics or distributed control. And bottom, you have a target assignment problem for M robots going to end destinations, and at the top, you have a formation control problem where you throw a bunch of nodes and you ask them to make a sort of a grid in a sort of self-organized way. The other half has to do a little bit more on sort of genetic identification or metabolic network identification for systems biology. And perhaps the more recent thing is we're using some of the ideas from distributed control, from robotics and control, to control a bunch of E. coli, and using swarming ideas so that they can actually sort of rotate. They're attached to this metal plate, and they're trying to sort of create essentially a bioactuator. So this is not so much systems biology, but rather more the engineering of sort of biological systems, where you're trying to sort of create engineering systems out of biological. So unfortunately, that would be not part of today's talk. Today, I'm going to talk more about cyber-physical systems, and I'll mean this in the broadest sense. I mean information systems merging with the physical world, or if you like, there can be more narrow definitions of computing and control systems or sensors and so on. A variety of applications, whether it's sensor networks, transportation networks, autonomous UAVs, DARPA challenge vehicles, or medical devices. There's been a lot of discussion as to what are the grand challenges in the area of cyber-physical systems. There's been a lot of workshops, both in the US and Europe, NSF, and in fact, there's a new NSF program on cyber-physical systems. And these have been not just my kind of take on what are the research challenges, but in fact, there's more like community consensus on what are some of the challenges of cyber-physical systems, compositionality, how do you put things together. You can think of sort of a component-based engineering, robustness and safety. How do we make the interaction between the physical and the information world more robust? And we'll touch upon that today. Of course, control and and sensing, whether it's hybrid control, distributed controls, and distributed sensing. Rethinking computing abstractions. So this is more of a challenge for our friends in computer science about making computation a little bit more time aware or energy aware and so on. And something else we'll talk towards the end, if there's time, we will talk a little bit about how to bring, in some sense, the world of control computing closer together. Again, these are high-level grand challenges that one can think about. I'd like to motivate the rest of the talk with a particular example that we've worked in our lab, which we had these UAVs flying around doing formation control. And if you were to sort of zoom inside what happens inside the UAVs, there were essentially 3 layers. There could be more, but let's say for the rest of the day we have 3 layers. The middle layer is in some sense the layer of control, or the layer of MATLAB, and that's where you typically design sort of your controllers, your sensors, and so on. Then you have sort of a lower layer, which is where you map the controllers to some kind of embedded processor to do some kind of real-time processing and real-time scheduling of all the control scheduling, sensing tasks, and so on. So this is the case where computing, in some sense, implements or serves computation. But then you also have a layer of computation above, if you like, the control layer. And that is where you write software which sort of supervises lower level controllers. So essentially the controller, the sensing layer, is wrapped around a lot of computing. But I would like to sort of break it up into 2 separate types. One would be more like a supervisory layer where software sort of supervises a lot of controllers, and ideas from hybrid control techniques would be more relevant there. And the other one is where the control layer sort of needs to be mapped onto real-time computing, and that could be more the embedded or the real-time computing or real-time control aspect. So given this kind of architecture that you can see, of course, not just in our UAVs, but you see it in many other things, whether it's robots and so on, I'd like to abstract out 3 layers. And one would be the top layer, which I would call sort of a task programming layer, where we will use sort of software computing in some sense to supervise controllers or to sort of program tasks for our UAVs. And that would be one layer of computing. Then we have the middle layer, which is the control, where controllers reside, and that's the one we're very familiar with. And then there's the lower layer where we sort of typically implement in real time a lot of our control algorithms. So I'm not going to talk about any of these layers. I'm going to talk mostly about the interfaces between these layers. So I'm going to talk more about the interface between the high-level task programming and the control layer, as well as the mapping from control to real-time computing, because that's where I think a lot of some of the very interesting problems are on the interfaces really between control and computing in this sort of hierarchy. I'd like to argue that we should be thinking about making many of these interfaces more quantifiable and more robust. And then towards the end, we should think about how to bring things together, that will be the last part. So I'll start at the top, and the question then becomes, how should we be, if we think about a supervisory control language, if we want to program our UAVs or our robots, how should we program them? What should be sort of an appropriate task language? So we'll make, for today at least, the commitment that we'll be using. So this is the kind of setup. You have kind of a map of the world, and you have a certain robot, and maybe you have certain regions of interest, and you may want to have a search and rescue kind of a task. You wanted to visit certain regions in a certain order, avoid certain other regions, and so on, maybe be searching for something. So how do we formalize this? How do we write it in a formal, precise way? And we have been using temporal logics as a way of formalizing such tasks. So this is something that our friends in computer science have used these temporal logics to specify properties of computer programs, but we'll use them here to specify properties, say, of robots. So you can use a diamond to say, for example, eventually P2 will be true, the region P2 will be true. So that means eventually go to P2, and you cannot have other types of specifications, such as go to P2, P3, and P4. So therefore you can express coverage or sequencing. You want to go first to P2 and then P3. Temporal logic essentially is being used to sort of specify sequences of events and actions. And you can have also, you would like to go to P4 while avoiding P2 and P3 or P3 and so forth. So you can have reachability with avoidance. Now the important thing about temporal logic, or whatever other specification mechanism you choose, it doesn't have to be temporal logic, is that it should be compositional. And that is you can build more complex tasks out of simpler tasks. I think that should be something that any language you choose to describe your favorite tasks has to be compositional so that you can potentially at least scale and you can sort of do more sophisticated potentially tasks. So, then having this sort of preamble, I'd like to motivate a simple problem, which is sort of given a robot, and that's where we design our controllers, and given some task that a higher level would like us to do, how do we sort of say, you can think of a problem of mission or task planning, how do you design the trajectory that will take me from A to B, or satisfy the temporal logic formula, or you would like to think of potentially a controller which will, in a closed loop way, satisfy the specification. So there's a particular fragment of the logic that caught our interest, which comes actually from the area of hardware design. And this has been used in the area of hardware synthesis, in fact, which is the nice thing about this fragment, which is known as general reactivity 1, is that it is broken up into two parts. There is a part of the formula that has to do with the assumptions of the environment of the robot, and the other one is what we would like the robot to satisfy. So this is the typical assume guarantee that we'd like the robot to satisfy this if we know that the environment, we assume that the environment will satisfy this. Now the environment could be the environment, like we know that Alex is in one of the rooms, that could be an assumption, or it could be something about another robot. So this allows also to think about multi-robot specifications, where we know that we'll achieve something, assuming that our other robots will achieve something else. It can also be a human, potentially. So there is a nice assume guarantee structure which very naturally expresses many tasks in robotics. And if I zoom into each of the sides here, there's further structure, which I'm not going to go through. It can get quite hairy, but it's sort of broken up into the structure in the initial conditions, the allowable transitions on what we know about how the environment may evolve, and goals for the robot, and so on. Of course, if we don't know anything about the environment, we simply replace this with the formula true, and we just don't know anything, and we plan for all possible environments. So the good thing about having environment assumptions or sensor assumptions is that you can sort of easily, or maybe not so easily, but sort of express simple search and rescue missions in this language. And so basically you break up your atomic propositions into sort of sensor propositions, whether you have seen somebody or not, and sort of output propositions, which is what rooms you would like to visit. Yes?
You consider that those initial conditions, you don't know anything about the environment.
True. True at your initial state of the environment is true.
But it's not.
Then you just model it here. If it is not, you can capture it here. You replace this formula with whatever constraints you know at the beginning about the environment. Exactly. So the explorations happen here. This is how the environment may evolve, and this is how the robot may evolve. So both are captured. And it's amazing because it's really a structure that comes out of hardware design, and there are ways of translating this into Verilog, basically. And it's quite nice that the same kind of thing can be used. Now, we also have translators, and we're working with some of our computational linguists to sort of take actually textual descriptions and get this automatically so that people don't have to do these ugly things. So now the question is, how do you design a controller to satisfy all this stuff? So the approach that Hadas has done in her thesis is to use correct by construction. So we'll take it top down, starting with a formula. There are ways of converting the formula into essentially automaton, and you can think of the automaton as being essentially your discrete controller, or the controller at the symbolic level, where you can say, well, you know, the specification says start at room 12, which is somewhere here, and then this says, well, you should go to room 9, you should go to room 1, and then if you see Nemo, you beep. If you don't see Nemo, you go here. So the whole plan is basically here. It's constructed for you automatically. And one of the good things about the particular structure we used is that it actually, because of the particular structure, it's not a full fragment of LTL, which is expensive to translate from the temporal logic to the automaton. This can be actually realized in polynomial time, where the number of steps is polynomial to the number of input and output propositions. So the complexity of this is in some sense much more dependent on how many input and environment propositions you're putting into the automaton. We have done this And we have been able to get automata of 50,000 states or more. So it is way within sort of the kind of tasks, at least, that we were thinking about doing, at least in the lab setting. So now this is just a discrete feedback, and you have essentially the discrete controller, but you need to get sort of controllers out of it, physical controllers out of it. So then the next question is, how do you go to the physical layer? And that's where we use some kind of controllers that have existed recently in the hybrid systems literature, which basically says that if the high level or the discrete level says go from room 9 to room 12, the high level doesn't know exactly where the robot is in the physical world. So you need controllers that regardless of where you are in room 9, you should be going to room 12. So you need this kind of so-called bisimulation property that we have seen in the world of hybrid systems. And this ensures that whatever trajectory or whatever actions you take at the discrete level, step by step, you can sort of match at the physical level. And if you sort of essentially couple all these things together, what you get at the end is essentially, you plug in controllers like this in each of these modes, you get a hybrid controller. And the hybrid controller essentially at the end is the closed loop hybrid control system, satisfies the specification if the specification is realizable and feasible by construction. So there's no verification to be done. It's really all synthesis, and it's by construction. And the assumption that this system will operate well is true only, of course, if the system operates in an environment that meets the assumptions that we included at the beginning. Okay, so if the environment, we operate in an environment and those assumptions were not captured in our design, then we don't have any guarantee. The system may still operate, but we cannot offer any guarantee. Okay, so how to design such controllers. There's plenty of them actually out there. Here's a couple. We have, in fact, used Dave Connor's controllers because they're a little bit more robot-friendly when we actually use these in the lab. But there's plenty from a correctness point of view, they're both fine. So just to give you a sense of how well does it scale, here's an example that has about a few thousand states, so this hybrid automata, discrete states. So the specification is we have a bunch of cars. Remember, one car can be the environment of another car. And the specification is drive around and look for parking spots. And if you see parking spots open, just park. Otherwise, keep on searching. And some other cars are simply going through. And by the way, in the meantime, you should obey traffic laws, which is stop at red lights, as well as do not collide with others, and so on. So all of this was relatively, it took some time to do, but I just want to tell you that even though theoretically maybe the complexity of this algorithm may be polynomial in the number of states, which is exponentially the number of variables, still, for a lot of these kind of problems, the size is still okay. So we are, and again, we do not have to verify anything. Things are correct by construction. And in fact, it was not that difficult to go from this example to the semifinal run of actually the Urban Challenge last time. So Hadass took actually the root definition file and the mission definition file for the Urban Challenge. This is not the full Urban Challenge. It's actually just the semifinal. And in fact, this was, I think, simpler than the previous example. And it was easy sort of to kind of capture a lot of the specifications and construct a lot of the logic automatically and just use the controllers in this particular setting. So just give you a sense of kind of that even though we're looking at a restricted fragment of the full logic, the expressivity from the kind of tasks we can do is actually quite good. Now, I'd like to switch on something else a little bit, which is, now we did design a controller for a simple abstraction, a kinematic, say, robot or a fully actuated robot, and some people may complain that, well, the dynamics are not, the reality is not that simple, the implementation is not going to be close, or it should be a more detailed model, a unicycle model, or a mechanical model, and so on. So and that's a valid concern. So I'm going to assume for now that the lower two layers, that let's say that we have the trajectories, say, of the lower two layers are staying close. So let's say the trajectories of this and this will stay within some bounds. And we would like to know, for example, if this model satisfies the formula or the specification or the mission, will this also satisfy? Will it propagate down? So if you look at the world of sort of what I was presenting before, and this is the usual kind of thing that happens in computer science, is that we had a trajectory of, say, a physical system, and that's a trajectory of a robot. We had a mission, and then at the end of the day, we said, okay, the trajectory met, satisfied, or not the specification, and we have this sort of Boolean view of the world. Now, of course, we know that the actual system may or may not be close to that. So it could be, for example, within epsilon. And therefore, what we do not know necessarily is if the green one satisfies the specification, will the red one, which may be due to the more detailed dynamics or the implementation and so on, also satisfy the specification? And there's no necessarily, we don't have a way, at least now, to say whether the property propagates from the simple to the more complex problem. So this is essentially a problem of robustness, that essentially meeting the specification is not very robust to perturbations in the physical world. And there has been some work on thinking about robustness in the world of temporal logic. Much of it has to do with timing, robustness in timing, especially in the sense of timed automata and so on. And there is also some work with respect to state. And in some sense, what I'll talk about next is in some sense in the spirit of how will state perturbations affect sort of the satisfiability of the formula. So what we propose is in some sense a robust semantics for temporal logics, which basically says, pretty much intuitively what it says is that given a trajectory like the green trajectory and the formula, rather than saying that the green trajectory satisfies the formula or not, you say not only whether it satisfies it or not, but how robustly it also satisfies it. So you return essentially not a Boolean value, but actually a real value, and it's a positive number. It's positive or negative. The meaning of that, intuitively, is that that number, epsilon, captures the largest tube you can put around the green trajectory without destroying the semantics of the formula. So if it's true, you want to basically get the largest tube that also will be true. And if it's false, is it a robust bug or not? Because maybe you shouldn't worry about bugs that are not robust. So this is essentially the intuition, and if that number is 0, then you know that essentially your satisfaction is extremely fragile. Any small perturbation will basically switch you from true to false and vice versa. So how do you define such semantics? So here's one way, and this is essentially the key idea is you take just a simple formula, like whether the robot is greater than 4, whether it's to the right of this wall or not. Now, in the usual Boolean sense, if you're at location 5 and you ask, do you satisfy the formula P, then the answer is true. Okay, if P was 4.1, the answer would still be true, but there's no way of distinguishing those. So what we simply say is that the semantics, or the robust semantics of the formula P, which is x is greater than 4, evaluated at the state 5 is 1 because A, it's positive because you satisfy the formula. And also because you're essentially 1 unit away from the bound of unsatisfiability. So that number, if it's positive, it says that you satisfy the formula, and the number, the absolute value of the number, tells you essentially what's your distance to unsatisfiability. So you have essentially kind of like hybrid semantics, where you sort of keep two things. There's a discrete component, which is whether the number is positive or not. And the other number essentially keeps you your distance from satisfiability. And this also tells you from now how much more complex it will be to handle robust semantics with respect to Boolean semantics, because here the only thing you need to do is set membership, and here what you need to do is compute distances, essentially. That's the relative complexity of the rest. Once you have that, then you can do the rest in the usual temporal logic way. Now, the semantics are not Boolean. They're over the lattice of the reals, and essentially you can say that the robustness of negating a formula is flipping the sign of the formula. The robustness of two formulas is the maximum, of the disjunction of two formulas is the maximum, and so on. So, and of course, there's you can think of the until operator as sort of a disjunction over time, and you sort of look at the maximum over time, and along the way you look at the minimum of what you need to satisfy before the until operator, but that's technicality. Now, this leads to sort of a recursive algorithm, sort of a rewriting kind of algorithm, where given a signal, you can sort of apply this by induction of the formula, and you can compute. And what you compute is not exactly the robustness, but you compute an under approximation of the robustness. So you don't compute exactly what you want, which will be very hard, of course, given a signal and a formula, what is the largest tube. But you compute something that is sort of an inner approximation. And that can be occasionally a good thing to have. And there are fragments of the logic of LTL for which this is equality, especially when you don't mix diamonds and boxes. You can do some things. That's the million-dollar question. So there's a lot of problems there. One problem is, given an epsilon, is my system this robust? Another problem is, given the signal, what is the maximum epsilon? There's an analysis problem. Then there's a control problem. Design a system so that you meet the specification and maximize epsilon. There's a wealth, and there's a wealth of directions to pursue. So this was the first step, which is sort of saying, how do we think about robustness when you sort of think about physical layer robustness when you go from signal to symbol. So what you can do is you can look at sort of, no, there's plenty of people here, so of course not. So so here's what you can do. This is the formula at the top, and we could design controllers the way we designed them previously to satisfy that formula. And these are two trajectories that they both satisfy the specification. So from the symbolic point of view, they're equivalent. They basically satisfy the same sequence of symbols, but they have completely different physical realizations, and you can sort of compute and see that this is a little bit more robust, and you can see that you can fit a thicker tube around it, and therefore it's more likely that this will actually be realized as you go lower in the hierarchy when you actually put realism, or if you have sensor uncertainty and so on, whereas this is more fragile since it barely touches here. I should say one thing which was a little bit non-obvious to me, and that is robustness may increase with time. It doesn't necessarily monotonically decrease. So if you say go to the room, you can enter the room, or you can go to the center of the room, and you can make steps to increase your robustness along the way. And that may depend on how much, say, your localization uncertainty and things of that type. So there's things like that. But you can do other things other than just this. So here's another thing you can do. You can ask, I have a continuous time signal, and then I sample it with your favorite sampling parameter. And then you can ask, if I test that this sampled signal satisfies the mission, can I say something about the continuous time signal also satisfying that? Okay, so I'm not going to get into this, but the kind of the philosophy is pretty much the same, and that is that if you can say something about the relationship between the samples and the continuous signal, and the discrete samples satisfy the specification in a robust way, then you can sort of pull the kind of the satisfiability back to the continuous way. It's the same kind of philosophy. And another thing you can do has to do with our old friend from hybrid system, which is the computing verification and reachability sets. The problem is, given sort of a set of initial conditions, you want to compute the reachable set, and you'd like to know whether you touch an unsafe set or not. And there's a lot of very good ways of computing reachable set, but sort of the new point of robustness gives us a different way of looking at the problem, and that is, why don't we just simulate a trajectory, and let's look how robust it is, and let's assume for now that the system trajectories will stay within that tube, which is something we'll talk about a little bit later. Essentially what I've done is I verified a tube of trajectories, not just a single trajectory, but I actually have a tube. And now I can use that to sort of pick another initial condition to sort of sample, and I can sort of keep on doing that. And if I'm lucky, maybe I will cover the reachable set. Of course, this is simulation and testing, so this is a finite horizon. We're not looking at unbounded safety. So now, lucky means in this context that there is some distance between the unsafe set and the reachable set of the system. And that means that if that number is strictly greater than 0, then there's a finite number of simulations suffices to sort of cover the reachable set with these robust neighborhoods. And the complexity is not so much a function of the dimension of the system. This is for deterministic continuous systems, I should say up front. But it's rather a function of the distance, which essentially means that if this unsafe set is too close to the reachable set, you're going to have to spend a lot of simulations trying to figure out whether you indeed touch that set or not. But if this is quite far away, then you may be lucky, and with one simulation, with one very rough simulation, you may be able to show robustness. Okay, so this is sort of showing that robustness can offer also a different kind of algorithm potentially, and we're sort of exploring this. For example, you can look at sort of a 81-dimensional linear system, and what you can do actually is using temporal logic, so you can sort of specify some of these traditional rise time overshoot kind of specifications that we typically teach in introductory control classes. You can sort of teach them using such a specification. Then you can ask, well, will my system, will my controller meet the specification for all these initial conditions? And so then what you can do is sort of just simulate and try to compute these boundaries, these tubes. And in some cases, you can show that with one, for different values of rise time and overshoot and so on, with one simulation you can falsify the property. But in some cases, with just a few number of simulations, you can actually verify the property. And again, we noticed that, of course, by playing this, the number of simulations can go also very high, especially when the satisfaction of the property is very fragile to sort of noise in some sense. So that wraps this part of the talk. I would like to sort of move a little bit on the other interface, which has to do more with the interface between control and real-time computing. And so once you have done whatever you wanted to do at the top, now you have to implement it. And the question there is, let's say you've designed your PID controller, and now you want to implement it, and this could be sort of the software implementation of a PID controller. And you would like to know, well, how good is this implementation with respect to that PID controller? The way this is done now is you sort of go to MATLAB, you write your controller boxes and so on, and then you sort of map the blocks to C code, and then real-time, the workshop sort of tries to do using some kind of a scheduling algorithm and then sort of executes them in some order. You say, I would like this to run at 50 hertz and 30 hertz and so on. The problem with that is that it is very hard to sort of get exactly in what sequence and exactly when these pieces of code will actually get executed. And that makes it very hard to sort of analyze what will be the impact on control performance, especially if some of these codes are actually sort of big chunks of code and take some time and so on. So our friends in computer science have been advocating using sort of a different paradigm here, which is more thinking about time-triggered architectures where the model of computation is predictably simple. So it's basically you compute, you sense, you compute, and the important thing is that these times are predictable and guaranteed by the computation model. Occasionally you have to do this at the being over-conservative and being a little bit slower than needed, but you are predictable. And if you are predictable, then the good thing is you can maybe model your model of computation, and then you can potentially have a way of actually having a mathematical framework and say that this is the impact of this model of computation on the controller performance design or the network or the sensor and so on. So a similar kind of paradigm seems to be happening also in the area of control over networks, say, or sensor networks, where you have a similar kind of a setup. And I'll talk more about this, even though we started originally with time-triggered computation. I'd like to talk a little bit more about time-triggered communication today. This is more recent and more preliminary work, where we'd like to find out, you have some base controllers and you collect data from the network. Maybe you collect it here, you make some control decisions, you send them back to the actuators and so on. So there are some new time-triggered protocols. So wireless HART is one of them. One Wireless from Honeywell is another one that's coming out. The key idea here is, again, as I said before, that the time is sliced in time slots. And you can sort of use that slot to sort of send communication. Now, of course, there's one big difference between time-triggered communication and time-triggered computation. That is, in communication, you may lose some of the packets. And that I'm not going to address that here. It's something we're working on, but it is something it should be sort of something we can incorporate in the future. And then here's sort of an abstraction of such sort of a time-triggered sensor actuator, if you like, network. So you have potentially your plants. Okay, so you have a collection of plants, and let's say for today we have one controller, even though you can have potentially multiple controllers. And you have sort of nodes with potentially a radio connectivity graph. And we'll assume that one of the nodes can fire at any time in any of the time slots. Essentially, one of the nodes can fire, and then its neighbors will listen. And that's the way you can basically transmit information sense information from the plant, the controller, and then potentially back to the actuators. So you have essentially the plants and the controllers. You have a network, which is in the middle, which is how you relay information from sensors to controllers. And then you can also include in this model routing, which basically tells you inputs and outputs are essentially sensors and actuators, which gives you an acyclic graph of how, for example, sense data from here can go to the controller. It can go this way, or it can potentially go this way, and how you can go from outputs back from the controller, say, back to some actuator. So this is input, if you like, to the whole process. This is our model of computation or time-triggered communication, if you like. Now, given the routes, you can sort of maybe refine a little bit the graph. And essentially, the way that this works is rather than firing nodes, you can sort of fire the edges for reasons that have to do with incorporating the routing here. And essentially, at the beginning, you start with 1A, 4A. So node 1 sends stuff to 4, and then 2 sends stuff to 5. And then you do the same thing. And then at some point, the controller has all the information it needs, and it sort of fires, which means it does the computation with the latest data it received. And then it starts sending back information back to the actuator. And now you want to know whether there are any good ways. How does this impact the performance? Are there good ways? Are there bad ways? Should we be spending more time on some nodes or some edges and so on? So to do that, we need to model this. And the interesting thing is that if one looks at any particular time slot here, now I should have said at the beginning that plants and controllers for this part of the talk are discrete time linear systems. So if you look at any particular time slot, let's say this time slot, then the evolution in that time slot is governed by essentially this matrix. And that matrix has pretty much everything in the sense that it has the plant dynamics, which evolve at all times. It has the controller dynamics, but the controller dynamics are controlled by this discrete variable, which tells us whether the control is on or off, and so on. It also has a lot of the things that which controller is affecting which input. So these are the BC matrices of the controllers in the plant. And perhaps more interesting, it has part of the network, the adjacency matrix of the network right in the middle of this matrix. And the part of the network it keeps is only the edges that are active. So it could be the case that many of the edges are active. And those are the ones that essentially you keep that part of the graph, and you slap in the adjacency matrix of that network there. So this basically has the network, it has the controller, it has the plant, and so on. And now, of course, this is for one time slot. As you go around, as you change time slots, you're changing essentially which controller is active, and you're changing who's communicating with who. So essentially what you get is essentially a switched system. So the semantics, if you like, or the behavior of this overall thing is essentially one of a discrete switched linear system, where you have essentially two discrete inputs, if you like. One is the communication sequence, and one is the computation sequence. And within those matrices, you also have part of the network. So then the question is, what can we say? How can we say whether this is a good or bad implementation, and so on? So the way you analyze the impact, if you like, of the network is you are looking at the top, and the top is sort of your ideal implementation. So it's the controller that the control engineer designs, thinking that it has all the resources, all the implementation resources one needs. From the perspective, has a sort of a fully available network and so on. So that's the ideal design. And then this is the implementation. And then what we'll look at is sort of the error of the two, and try to see whether we can say something about the error of the two systems. The top is a standard discrete time linear system. This is a switched linear system, essentially. But the switching, in many cases, is periodic. That's the kind of standard assumption you see in scheduling. And in some cases, it's not. If it is periodic, then essentially this is a periodic linear system. And this is a discrete time linear system. And periodic linear systems, for those of you who take ECS 221A, things we can do. We have all these Floquet decompositions and all these things. We can do a whole bunch of things, lifting techniques and everything. So we can actually analyze those. And here are two ways of analyzing them. One has to do with thinking about periodic and deterministic scheduling. We did it originally for time-triggered computation, but it's the same kind of idea for time-triggered communication. And then there's another version, which I'll talk a little bit later. So if one sticks, in this case, in the L2 norm of the discrepancy between the ideal and the implementation, one essentially gets that the error due to the network implementation is essentially some kind of a quadratic form. In this case, you can compute exactly, in the L2 sense, what the impact of the error is. And it's some kind of a quadratic form, which depends on the initial conditions. And the way you get the matrix in the middle is by solving some kind of Lyapunov equation by getting this sort of implementation-dependent kind of matrices. You get a Lyapunov equation that depends on the scheduling and so on. So the one thing here to note is that the error is dependent on the initial condition, which also means that for some initial conditions, maybe this implementation may be better than another. You cannot necessarily say universally that this implementation is globally better than that, unless the quadratic form is globally better than that quadratic form. So it's a simple sort of a positive definiteness kind of a check to see whether one implementation will be better than another. The graph is hidden in the implementation-dependent matrices. We have not played at all with the problem of how do we control the graph in a way that maybe it will be better. Okay, so that is a very good problem, and we have not, we've just started with this, but that's a great problem too. And because the nice thing is that it's sitting in our face, in the matrix, and you can sort of maybe, we know something about the eigenvalues of those matrices and so on, and maybe there's something we can say about what the impact of the network is and how to control that. You're lifting to something, exactly, yeah, that's right. Yeah. So the price you pay with the lifting, of course, is that these matrices can get large. That's the kind of thing that happens. Okay, so you can skip this slide. Another thing you can do, and this is another reason why I think time-triggered architectures are very good, is that one is that it offers a formal model of computation, and therefore you can quantify the error. Another thing is that automata, you can model essentially computation is an automaton because it's a string of computation. And maybe if there's many options, it's an automaton. Automata are composable. You can take the two languages of two automata, you can intersect them. So how can you use that to have a compositional framework here? So you can have, for example, you can say plant one, and this is part of a toolbox here. So you can have plant one, which says, I have these control loops, this is the network topology, and this is my routing to the controller back and forth. And these are sort of my performance guarantees, and this has to do something with the rate and things like that. And what you can do is you can extract the language, which is essentially the collection of all strings, that will essentially allow you to achieve that kind of control specification. So you can either have a fixed string, which says this is the schedule, or you can have a variety of strings, which you can capture as an automaton. You can say, well, I can do sensor 1 now, and sensor 3, or sensor 5, and it doesn't matter. So you can have options in the scheduling, and all of that language satisfies this control specification. Then plan 2 can also come and do pretty much the same thing. You can say, well, I need resources from the network. This is my specification. Give me all the schedules that can actually meet that specification. Now, you cannot compute, it's very hard to compute this exactly what the language is. You can compute under approximations of those languages. And then you can simply take the intersection of languages, and that's the compositionality that automata theory offers. You can just take the intersection, and the intersection is a set of schedules that will satisfy both. And then from that, you can pick a schedule that could be, for example, the shortest path in that thing. So that's the kind of additional thing that time-triggered architectures offer, and that is the sort of the more compositional reasoning, which is very hard to do, for example, when you talk about worst-case execution times and sort of periodic tasks and so on. So this is another advantage which can allow you potentially to scale. And this is also important. You can think of this as an admission control protocol. If another plant comes and says, I want resources, you can sort of do this test and decide whether you should allow the plant to enter or not, and you should not allow it if the language is empty, which means that there is no schedule that can satisfy everybody. So I think I want to conclude with one last topic, and that is I've talked a little bit about the interfaces. And clearly, I've used it. You can see, so in some cases, we use automata at the high level, at the lower level. In the middle, we have differential equations. And I think a research challenge, as much as I would say also an educational challenge, I would say, is try to bring in some sense the models and methods of control and computing closer together. And to do that, one way of, you need some kind of a common language to describe all these things. And we can use the language of transition systems, and that we saw, for example, how temporal logic can be translated to an automaton. We frequently in hybrid systems, we take out differential equations and think of them as automata, or at least we write them as automata, and so on. So we can all think of them in this language of transition systems. And then in the world of computer science, there are ways of sort of relating models, and there's been a lot of work about whether sort of a automaton can simulate or do everything that a differential equation can do, whether a differential equation can do everything that a Turing machine can do, and so on. And so there's all these wealth of relationships that you sort of see in computer science. And the top left, you see is the notion of sort of bisimulation, or the notion of simulation, which here simulation basically means for every step that system S1 makes, system 2 can also make. So we've seen in some sense some of that in the hybrid controller synthesis. Then you have language inclusion, which means that for every trajectory of this is also a trajectory of that, and then the reachable sets are contained. An implication here means that if one system is simulated by another, then the language of one is contained in the other, then the reachable set is contained in the other. This essentially is implication. So we have all these things, and we've used those in the last decade or so in getting a lot of nice results. Now, when, of course, computation interacts with the physical world, we know that we're interacting with something uncertain, and just having binary relations and binary relationships between models may not be necessarily the best thing. So we should really be thinking about using approximations, or if you like, approximate relationships between models. And that's what we have been doing, in particular the work of Antoine Girard over the last 3 years, is to think about the notion of approximate simulation and bisimulation and so on. And this is, in some sense, is what the original goal was. And that is to think about pseudometrics in the sort of space of systems, where you essentially say that, for example, this one says that this is a pseudometric between these two systems, and it's 0 if the two systems are bisimilar. And if it's not 0, then you sort of want to have a degree of bisimilarity, how close to bisimilarity you are, in some sense. So the fact that when you say that when this is 0, this occurs, it means that we are already capturing, if you like, the traditional sort of hierarchy of system relationships from computer science, if we can define such metrics for systems. Now, to define metrics, you need a metric. So now we're going to think of automata where the state spaces are equipped with some kind of a metric. And that's where the notion of approximation makes sense. You need some kind of way to say whether two states are close or not. In the purely binary world, that may or may not be an interesting concept, but in many cases, it is. And when you deal with the physical world, it definitely is. So you can define language metrics, which basically means that this is simple, that for every trajectory of one system, the other system is trying to basically find a trajectory that's close to it. And you play this sort of behavioral game, if you like, where one system picks a trajectory and the other one tries to pick the one that's as close to it. And you look at all possible trajectories, and that's in some sense the language distance between the two systems. Now, I guess the more interesting one is the notion of approximate simulation relation, and the related, which would be approximate bisimulation. And that is pretty much the same as, for those of you who know the traditional simulation relation, it's pretty much the same. You play a game between the two systems. For every move of system 1, you have to do a move of system 2. Now, in the traditional simulation game, for every step of one system, the other system has to match it exactly. In this case, you just have to match it approximately. So given some delta, let's say the delta is given for now, you just match it approximately. So Q2 simulates Q1, for example, for any move that one system makes, the other one makes, and you sort of stay within delta. In other words, you start with delta close and you sort of stay delta close. That would be one way of looking at it. You can look at the tightest approximation, so the distance between the two systems, the approximate distance between two systems is the tightest approximation that one system can approximate the other. Okay? So that's how you eliminate delta out of the equation. And what you end up getting, cutting to the chase here, is you sort of get a hierarchy of metrics where you have a bisimulation metric at the top, a simulation metric up there, a language simulation metric. These are the symmetric versions, and these are sort of the one-sided versions, where rather than saying that one implies the other, the arrows here mean essentially that they're upper bounds. So for example, this is an upper bound for this. This is an upper bound for this. The simulation metric is an upper bound for the language metric, and the bisimulation metric is an upper bound for the simulation metric. So what you have is essentially not a hierarchy of relations, but a hierarchy of metrics. Now, the interesting thing is that when you set the bisimulation metric to 0, everything else becomes 0 because it's an upper bound, and you extract the hierarchy that we had at the beginning. Now, the other interesting thing is that how do you compute some of these things? Because that's really the challenge. So the way you compute some of these things is that, for example, to compute the simulation matrix, you get a Hamilton-Jacobi-like iteration here. So you play a game between the two systems, so you get a generalized Hamilton-Jacobi-like equation. And once you compute the value of a function in that space, then you sort of play a static game where the solution of that dynamic game becomes essentially the value of this static game. Of course, this may be a little bit hard to compute. So what you typically do in such cases is you sort of look at Lyapunov-style relaxations for such things. So you're looking for functions that can bound from above the value function. So if you're trying to figure out, for example, whether two systems are bisimilar, approximately bisimilar or not, and what the distance between the two systems are, then you're looking for some function that sort of bounds the observational distance, and then you sort of have this kind of game between the two systems. So you want essentially the function to be an upper bound for observational distance, and also you want this function to be an upper bound for the future evolution of the progress. So if Q2 simulates Q1, then the successor of Q2 should also simulate Q1 with the same approximation. So the value of that function does not increase with the evolution of time. So this is essentially Lyapunov-style condition. So if you actually restrict it to purely continuous systems, that's exactly what you get. Okay, so you have two systems and you want to ask with disturbances, and you want to ask, are these approximately bisimilar, and how much? How close are these two systems? What you end up getting effectively is you're searching for a function that satisfies essentially this Lyapunov game. So you're searching for a function that essentially upper bounds the difference between the observations. And it does not increase with the evolution of the system, subject to this game that is usually a standard game that you see in bisimulation, that one system picks a move and then the other system tries to match. If you can find such a function, which is the kind of things we do in control theory, then you can say something about the distance between these two systems, which may potentially have different disturbances, different outputs, and so on. So I guess my final point, for all of this was that you can, if you look at what we have achieved with this, is that we've developed this hierarchy of metrics, which when you set them equal to 0, and you apply them, say, to discrete systems, automata, you sort of essentially extract the hierarchy that people in computer science use for sort of simulation and bisimulation relations and so on. But when you sort of, say, look at it for continuous systems, when you just look at, sort of instantiate the definitions for continuous systems, then you try to find bounds, and you get Hamilton-Jacobi type equations and or Lyapunov-style things. So the point here is that it serves as a very nice way of when you take these ideas and you take them to sort of a more quantitative level, then it's a lot easier to sort of connect methods that we typically use in control theory with methods that our friends in computer science use on a daily basis. And that could serve definitely as a unifying way of connecting the two. But you can also do a lot of other things. For example, you can ask questions like, when does an automaton approximately simulate a differential equation and so on? And there's work in that direction. So I'm going to conclude here and just say that the emphasis here has been really on the interfaces. There are toolboxes for everything I've said. So there's a toolbox that does the LTL synthesis. There's a toolbox that does the robust testing and the robust simulation and robustness analysis, as well as a toolbox where you give it sort of the PID controller and some kind of a schedule or a platform model, if you like, and sort of computes, if you like, what the error is and what the impact is and gives you the quadratic form. I'd like to, reemphasize this, and I'll just conclude by thanking Alex and everybody for your attention. So thank you very much.
Thanks a lot, George. So in the tradition of the lectures, we're happy to present you with the plaque of the lectures. And I think we have a couple of minutes to take questions from the audience if you have any. Yeah. Claire, do you want to go first?
Yes.
In the work that you presented on robot motion planning, and in particular looking at the interface between the tasking language and the control, sort of the control, I mean, I think it's really interesting, and you sort of hinted at this in talking at the interface, to think about ways to task or ways to design your tasking language or the kind of words and alphabets that you would use so that so that it's inspired by what you know the control can do below it.
I completely agree. I mean, the hierarchy presented was completely top-down.
Yeah.
So there are two reasons for that. One is that I think there's a well-defined language, a linear temporal logic, which we can argue whether that's a good or bad. That's not the main point. It is compositional, and there are a lot of tools that one can use to scale. I agree with you that one should go bottom-up. And the bottom-up is the more like you have controllers, and then you want to basically sequence it, because that's essentially what the control person gives you all these controllers. Whereas in this case, we designed the controllers to sort of fit the automaton.
But I think what you presented would be more, it's interesting to think more about both like a bottom-up meets a top-down.
I agree. The challenge always is a little bit, I mean, you can do that in this case. So for example, somebody can say, here are the controllers, here's what I can achieve. I can go from room 1 to room 2, but not from 5 to 6. And you can trim your automaton to eliminate some of those things that are impossible at this level. And you can do that. I would even say that one can do even a little bit more in the sense of you can design a language where the atomic primitives are not so much room 1 and room 2, but track a person with these parameters and so on. The challenge with that is making it compositional. And that's really the challenge. The technical problem is how to make it compositional in a verifiable way. Because remember, this was in a verifiable. You can make it compositional by stitching controllers together, but then the question is, can you offer guarantees by the composition? Right. But I agree with you. It's a good question. Yes.
Hi. I want to ask this related question about this hierarchy which you presented.
Yes.
So you presented various ways of achieving robustness, quantitative verification. Yeah. How do we distribute robustness between different layers? Why and if the robustness margins are actually measured, how do we actually achieve trade-off between distributing robustness? That is the first question. And the second question is about your assume guarantee approaches, where you assume you guarantee the assumptions. So how do we actually make specifications about the environment? So is that a solved problem as to how to achieve?
No, it's a modeling problem.
Okay.
I mean, the environment you have to model. You cannot get away from that.
Right.
Let's start with the easy one. You just have to deal with it. You just cannot walk. I mean, you can blindly say that I know nothing about the environment, put the formula true. The price you're going to pay for that, you're going to be planning for all possible contingencies, and that's going to create a huge plan. So the more you know, the better you're going to be. But you're not going to get away from modeling the environment unless the environment is artificial, where, for example, the environment of one robot is another robot, and you know something about the other robot will do because you've designed it and so on. But if it's a physical world, you may have to do this. Now, something that's there is that my environment, at least in this talk, was binary. And there's a lot of work which is skipped, and I think which is how do you go from physical sensing to sort of binary sensing, which you can feed here, or how do you incorporate physical sensing into this mix? I think that I didn't touch. It's a big problem, and it's something that needs to be done. The first problem, the problem you mentioned, was about the hierarchy. How do you propagate it from one to the other? So, for example, one simple answer here in the setting is you design a controller to meet this sort of a plan, but then we discussed later that the trajectories will stay within a certain bound. Why will they? And so we have to make sure, for example, that when we implement them, for example, they stay within that bound. And if they do, then I know that if I design this for the task, then this will also, so for example, meet that. If you don't do that, in fact, we come exactly to the problem that you mentioned, that essentially the property doesn't propagate down the hierarchy. Agreed. And in fact, I would argue that you need robust compositions of such systems to be able to essentially go down the hierarchy or across a distributed system, if you like. But both very valid points, yeah.
I guess my question is along this line. So yes. You say that you don't need to verify the system. You had the simple double integrate of the robot, right? Yes. And then you say several times that once you have your final automaton, then you don't need to verify the system. But the main assumption in there is that basically once all the states of a mode can be brought really in another mode.
Yes.
So your local invariant is infinite. It's basically all the space. But you're assuming there exists a controller that would bring
right.
you...
The top-down puts a lot of burden on the down person because I'm pushing essentially the specification to the controller, and because there are very good controllers these days, now if the controller person says I can't do it, then that's when exactly the same question was. Then you have to basically start propagating things up and say, sorry, I cannot do this part, and so on.
Okay.
I agree that this framework is extremely top-down, which puts all the burden on the controller. And for some classes of, say, polytopes and so on, you can design such controllers for x dot equals u. But if you have more complex dynamics or more complex sets, you may not be able to do that, in which case you're going to have to do. But still, I would like people to be thinking along this kind of up and down way. Yeah, that's, you can go, bottom up. That's okay. I have no problem.
And your theorem, maybe we don't have time, but should I use your theorem or should I just do, regarding robustness, so
yes.
should I just do a forward reachability analysis, set reachability analysis, and compute the distance to the unsafe set? So what does the theorem, forward or backward, depending which problem I want to solve? The theorem regarding your robustness level
for the temporal logic.
For the temporal logic.
So whether.
So if I do a set simulation of the hybrid
temporal
system.
logic is typically, the temporal logic I present is forward temporal logic.
Okay.
So the until and the next operators and so on are forward. There is a temporal logic that looks backward in time. So, I satisfy formula now. If 3 steps back, I saw something. And I don't think it's a big issue to do it backwards in time as well.
Okay.
I don't see that's a big challenge. Typically going forward, backward is not as challenging. Yeah.
So the first slide, was that an experiment where the E. coli were moving the...
Yes.
Was an experiment?
Yes, and I can show you another experiment where essentially you can think of it as a robotic, a biological robot where we're sort of doing like a biological version of sort of a peg in the hole. So you have a hole and you want the bacteria to sort of steer the plate into some sort of...
Can you show it again?
I'll show you something. Oh, sure. I'll show it to you.
Or something...
No. Okay. So this is it. So you have a whole bunch of bacteria attached to the plate. When you throw light at them, bacteria get knocked out, you stop. So that's your on-off switch. And then by using chemotaxis and magnetotaxis, you you cannot, of course, control thousands of bacteria. But what you essentially control is a little bit the average properties of these thousands of bacteria in a way that it sort of produces a torque so that they steer this around. So you give them essentially food or magnetic fields or light, and you sort of they essentially control the plate. Yes. Yeah. And the light, and So. Yeah.
Okay, George, I have been very attracted to your notion of compositionality. As we all know, that works for linear systems. What would be your suggestion to deal with nonlinear dynamical systems? I am particularly interested in, let's say, I have a model of one hand and another hand, or one body, and then I connect with another body.
Yeah, the compositionality I presented here is not at the physical layer.
It's not at physical.
It's not, you see, the compositionality. The assumed guarantee compositionality I mentioned was at the logical level. If you satisfy a task, I will satisfy a task. So you have essentially dynamical systems, and then they satisfy tasks, and I have compositionality at that level. If you want compositionality at this level, you really are going to have to look at the physical interactions, and that's a much more challenging topic, as you probably know.
That's right. That's exactly what I am facing.
Yeah.
So but it seems to me then maybe one can deal with the kind of piecewise linear modeling of these nonlinear dynamical systems.
So here's something. This is speculative. So. One way of potentially addressing it is, again, compositionality in the computer science world especially is very binary.
Of course.
Right?
Yeah.
So now if you make composition more robust or quantitative, and you can achieve, say, compositionality for linear type of interfaces,
right.
And those interfaces are robust in whatever sense, which nobody knows exactly what that means, then maybe the nonlinearity is within those bounds, so that if the linear compositionality holds and it is robust and the nonlinearity is within the bounds, then maybe you can say something about. But again, in that case, I think robustness would be a key to make robust compositionality. So I didn't talk really about robust compositionality, and I think if we have a framework for robust compositionality, not just compositionality, that may be a way to addressing that.
Yeah, thank you.
well, I think we should really thank our speaker for the wonderful talk, and so thank you very much, George.
Thank you very much. A pleasure.